Hi, my name is Aaron. I'll be introducing our speakers this afternoon. Right now, first we have Scott Orca from Merle, presenting on robotic manipulation with the Delta robot.
Great, thank you. So I'm just going to put this down because I'm plenty loud. I hope you can all hear me. So at Merle, I spend most of my time working on vapor compression, and my fun time is playing with robots. So I'm going to talk to you a little bit about this robot that we built. It's this Delta robot on the left that we named Kamaji after the Japanese spider in the movie Carried Away. So he's very dexterous, and I'm trying to make my robot like Kamaji. So what we're interested in doing is robotic assembly, and robotic assembly is basically a series of controlled collisions and contacts. And so I'm trying to do two things. I'm trying to build a robot that's good at collisions and contacts, so it has some advantages over a more conventional robot. And I'm trying to actually model contacts and collisions in some sense mathematically sufficiently correct so that I can put Lego together. So it's kind of ironic, but so the robot, we got it to play chess over the summer. It's pretty fast. It's very fast, actually. But it's moving pretty slow because otherwise it'll throw the pieces around. Anyway, you can see how it works. And of course, this is a Modelica conference, and so a lot of the work has been done using the Modelica language and sort of a combination of mathematics and the Modelica language. So Delta robots are becoming more popular now that there was a patent on these that expired about 5 or 6 years ago, maybe 10. So on the right, they are closed chain kinematics, and so that makes all the math a little harder, but not impossible. The advantages are primarily that they're very low mass, low inertia, and so they move very fast. And so when we're doing assembly of things, we want to have a very low mass manipulator so we don't wreck what we're trying to put together. So obviously, conventional robots do some assembly. They have a lot of mass, they have very high friction joints, they move very slow. Honestly, the dynamics of contact and collision is neglected. We're more interested in using a very low mass, low impedance device that can be very safe, but also very precise at the same time. So most robots are used for sort of pick and place. I should say all, and they're just controlled with a bunch of PIDs, very simple. So this is how pancakes are made, if you ever wondered. The robot just picks and places them up off different conveyor belts. But really, the goal here is to design some kind of nonlinear control. So the first step is to feedback linearize the robot and do impedance control of the robot. So that's done. And then the second step is the probably more interesting one. How do I cause the robot to assemble something? And so we're trying to actually model the physics of contact and collision to do that. So the Delta robot is challenging because the forward kinematics, which is the map from the joint angles to where the end effector is not explicit. You can't write it down in closed form. You have to write it down as an implicit set of equations. And because of that, everything gets a little bit more complicated. One of the fun things about this, I'll go through this kind of quick. So probably 5 years ago, I figured out a way to model this as a set of differential algebraic equations, and you can embed that. There are a number of ways to represent these. It's not unique. I like to sort of represent the dynamics of this in a higher dimensional space, and then you get a set of, essentially at the bottom, sort of 18 equations and 18 unknowns as a degree 1 DAE, which Daimola loves to, or any open Modelica too, likes to simulate and handle without a problem. So one of the interesting things about this robot is it actually has two different Jacobians, if you know anything about robotics. The Jacobian is the map from a force applied to the end effector to the joint angles and the joint torques. And so one of these robots we use for, one of these Jacobians we use for simulation, and you can actually write that down in closed form. Here it is. And that just maps a force to all the joints. But the control Jacobian, which is what we need to do control, which is the map from the motor torques to the force, this cannot be written down in closed form, and so you also have to compute it as a solution to a set of nonlinear equations, and so you can only compute this numerically, algorithmically. So I think people will understand this. This Jacobian should not be used in a simulation because it's an algorithm, and you don't want to put an algorithm which has got a termination condition inside of a smooth model because it'll cause the solvers to get a little annoyed. So we use the other Jacobian when we're simulating the effects of force, and we use this to control. So really what makes this robot interesting is its low mass and low inertia and very high speed, but also the fact that you have to use a lot more calculus to do things like computing its Jacobians. And so I've shown you a bunch of math, but of course, our language that we all love, Modelica, can easily handle this equation-oriented type of model. And so this is the full model of that robot. We just instantiate each arm and then write down a constraint equation that all three arms come together at the wrist. This is an index 3 DIE. The tool can then reduce the index, or I can sort of manually reduce the index by modifying these equations a little bit. And so it's very, very compact, of course, representation. So one of the fun things about this robot is it has all sorts of weird kinematic singularities. And one of the singularities happens, of course, when the arms are all straight out, right? But another one happens when actually, hopefully the animation works, when these the 6 parallel links at the bottom here all become, there it goes, parallel themselves. So if you kind of move it into this configuration, then it's really singular, and it just becomes sort of a spherical pendulum. It's useless as a robot. And what's interesting about this is that the model that we have is global. So the model can simulate through these singularities without any problem. Of course, you can't control it through a singularity like this, but we can model it through the singularity without any problem, and that's what you want in a model. So one thing I've done, you can feedback linearize this thing. So robots are relatively straightforward to feedback linearize if they're serial link robots. This you have to do more work. You have to do some calculus, and there's a bunch of implicit function theorem and all that kind of fun stuff. But when all the dust settles, you can actually sort of write down there at the bottom, and I won't go through this because it's pretty awful, a control that will make the dynamics in the task space look linear and in any sort of direction. So sort of X, Y, Z, it looks like a decoupled linear system. And then in the outer loop here, I can modulate the feedback gains to change the robot impedance. And so now I can have nice soft contact with something, especially when I don't know where it is, by making it very low impedance. And so I won't go through all the math. But this is what it looks like in, this is Dymola. So here I have the robot dynamics in the middle here. Actually, we modeled the dynamics of, say, a Lego brick. I'll talk about that a little later. And the green things are the control. So the control, because all these functions need to be computed implicitly, all of that has to be implemented in discrete time as algorithms. And so every green box here is actually implemented as functions in discrete time. So it's a sample data system, which of course Modelica handles very naturally. So you can see the clock here down at the bottom. We use the synchronous feature and the synchronous library. And one can run simulations, and you can see some simulations here on the right, of course. So the fun thing we did was, and I think probably this is the main message here, is I had an intern just before the COVID time come and write an interface from Dymola, in this case, using the device drivers library to the actual robot that we built. So we wrote some C code to glue it together. And then what we do is we can just unplug the model of the robot, plug in his little interface, recompile it, and run a real-time experiment of this nonlinear controller moving the robot around. And so I think this is nice. We could get it to run on a, this is like 2018, on sort of a vintage 2017 decent PC. It's all running in Windows at about 500 hertz sample rate, which is pretty good. And especially for like an academic lab, or in this case, in this example, Modelica, I said this yesterday too, you can use Modelica as a language to represent the physics, to structure the physics, to design, realize controllers, in this case all in discrete time, and then do a laboratory experiment all on the same platform. Never have to recode anything, which I love, because I really don't like coding. Or recoding, I should say. And so this was fun. He finished it the day before we closed down for COVID, and then the robot sat there for a year and a half and wasn't used. But you can see we hooked up a joystick, again, through the device driver's interface, and could make it move around, and it has really nice tracking, and that was kind of fun. Now, at some point, this becomes very limited, because all this is running on a single core, on a single thread, and we could only get it to work at 500 hertz. And I wanted to get it to run a little faster, so I rewrote all the code in C. I sort of hand-coded it. It's not that hard, because we'd written down all these functions in Modelica anyway, so we just sort of translated it to C and wrote it multi-threaded. And so now we can run this thing much faster. It runs at about a 90 microsecond sample time, like 10 kilohertz. If you wanted to, we run it around 1 kilohertz, which is the sample rate of all the servos. And it's sort of the various processes are split up on these two PCs depending on what we're doing. So we're now starting to use some touch sensors and play with assembly type problems. I'll show you. Well, I'm not going to show you it moving. I already showed you that. One of the tricks that we came up with is to modify any wind up a little bit so that we can. So when you're doing robotic assembly, if you have integral action in the outer loop, and you come in contact with something, that integrator is going to wind up and you can get bad behavior like this, right? And so normally the integrator is turned off in these robotic applications. Actually, if you implement the anti-wind up in this way, you can leave the integral action on, and when it comes in contact, you don't have that behavior. So that was kind of fun. Another kind of cool result, and I did all these simulations in Modelica, is to simulate the effect of using touch feedback on the robot impedance. So this is kind of fun. You can actually reduce a robot impedance with touch sensing feedback. And you can only reduce it in the bandwidth of the sensor, but it's actually quite significant. And so if you go up there and you touch the robot, it feels like it has actually much less springy feel to it. You can't do anything about the mass, but we already reduced the mass with the actual robot design. So I'll skip this. There's an animation from Dymoa, and here's our touch sensors. And so it's got very soft, a very soft feeling. I think there's a movie here it should run, and maybe not. How much time do I have? I don't know. Oh, great. Okay, I better speed up. So it's very low impedance, and the whole point here is that when this thing contacts, suppose it's holding something and you're trying to plug something in, you want to have very soft, low impedance robot, not stiff. So if there's a little bit of uncertainty, nobody gets hurt. I have it playing chess. You probably all saw that video of that poor Russian kid who had his finger broken by the robot chess player in Moscow, 6 months ago. This one won't do that. Anyways, so it's probably enough of that. We're trying to look at this assembly problem. And so I have a different point of view on robotics, maybe. It's much more model-based design approach. And so I'm actually trying to model contacts and collisions among different types of objects. And I realize that this is actually kind of like what Dirk was talking about this morning. A lot of the modeling paradigms are actually missing the dynamics of collision. So I've been spending time looking at how to model that in a way that is essentially, you end up with a hybrid or multi-mode differential algebraic equation type model, which is perfect for Dymoa. We have a lot of contact and collision problems, that's not important, but this is the main kind of slide. So when I have different objects, I have, physics, it's just a multi-body equation, so it looks like a big, DAE over here on the left. And when they're in contact, then you get a constraint, right? And what we do is we combine this model here on the left of differential algebraic equations, and we switch on and off these constraints depending on if you're in contact or not. And how do I decide if I'm in contact or not? Well, there's this finite state machine in the upper right. I did write a paper on this like 3 or 4 years ago that was wrong. It had missed a few of these states, but we fixed it now. And actually, this is a very effective way to model contact and collision. And it's very well suited to Modelica because Modelica has this nice hybrid model of computation. It's got an excellent state event detection. So essentially when two things come in contact, the state machine will change state. And I'm sort of busy trying to figure out how to properly formulate that. But here's an example that turns out to be quite difficult to simulate. Otherwise, it's this Newton's cradle. And if all of the balls are touching, but no force between them, these sort of LCP methods that are popular in physics engines from computer animation, they fail. And they fail for the reason that Dirk explained this morning. They're missing the physics of the wave that propagates through a set of materials. If you model it this way, we have a very simple model of the wave that propagates through those materials. So you get sort of something that is more correct. And this is important when you're looking at contacts and collisions. So this is a sort of more details. So when two things come in contact, they either stay in contact or they bounce off, and so you can model that bouncing. And if they stay in contact, we can make that sort of, it's a little bit like a spring model, make it soft so that this is actually not a stiff BAE as it after the collision occurs. So I'm still kind of working on this math. But kind of like as I said yesterday, there's a lot of math and there's code that I don't show a lot of, and there's two different views of the same thing. I think it's important to have two different views, right? Sometimes icon, you don't see a lot of that here. Sometimes it's math that you see a lot of here, and sometimes it's code. So here's the model of bouncing ball, and it sort of behaves as it should. So you have a finite state machine together with a set of differential algebraic equations. The structure of the equations changes, but the number of variables and the number of equations is always the same. And so this is actually perfectly well suited to the modeling language. Here's a sort of toy example where this brick falls and touches, and there's a lot of events, which is fine because there are a lot of events. And so it kind of goes through all that. The compilers, both OpenModelica and Dymola, handle this all beautifully. I sometimes think, oh, I'm going to miss an event and it's going to be a problem, but they're very robust. So skip that, and maybe I'll just mention this and I'll stop. So one nice thing about this model is it's actually continuous, and so you can show that there exist solutions. Most models of contact and collision claim to be discontinuous. There's a jump in the velocity. And that's because of the modeling paradigm that they've chosen, not because the actual physics is discontinuous. This is a different modeling paradigm, and it's continuous. And it's very much what Dirk was talking about this morning. You get stuck in your context, and then you realize that that's the only physics, and you think it's discontinuous, and actually, no, it doesn't necessarily need to be. And it's nice when things are continuous because it's easier to solve. So we've done a bunch of toy problems. I won't go through all this. Sort of the next step, and this is my last slide, is to put these ideas together and to use, so I can simulate things moving around now. I want to actually use this model to synthesize control that will assemble objects. And the sort of one piece that's missing that I didn't talk about is this concept of what's called a distance field. Distance fields have been used a lot in robotics for collision avoidance. I'm actually going to use them to cause the collisions we want to have to assemble something. And so I'm sort of busy realizing that in Modelica in sort of a library, so we can not only simulate an example of a robot, but actually sort of structure the math and synthesize new types of controls. So that's my user presentation. Yeah, it was a lot of fun giving these. I appreciate having the opportunity to talk about this and not have to write a paper. I like writing papers, but I'm many papers behind, as some of you know, and it's embarrassing. So I'll stop. Yes?
Yeah, I'm trying to come up with like an understanding directly from like I want to read it afterwards.
Yeah.
Would you say that another way to explain the approach here is to say that, like for example, solving a nonlinear system could be represented as when you use that solution in steady state. Solving LCP
Yeah, we talk a lot more about this. So in the LCP formulation, what happens is you take some dynamics and you discretize them at the beginning. Okay. Now, once you've done that, you totally forgotten about the continuous vision, right?
Yeah.
And then, okay, so here. Oh, I just must have had a collision between here and here. So I kind of back up a little bit, right? And I solve an LCP to figure out what all the steady state contact forces are, right?
Okay. Yeah.
So and it took me a year to figure out the dynamics of being ignored. It's very much like what George was talking about this morning, which is why I was all excited. So, this point of view, it's not correct to say this is more correct. I am solving a set of a couple VAs that switch, but I'm using the solution to figure out what that steady state is. Okay? So it's a way to, almost a way to solve the LCP problem, right? And actually, from linear.
Yeah, and we look at this in a case with many collisions, like,
Yeah.
throwing a bunch of balls together.
Yeah.
I think that one of the big things that people look at, right, is that, you have a lot of the,
Yeah.
the AI that did, right, the tools and stuff you mentioned, right, and they're able to handle many collisions together because they get a lot of collisions together. So I wonder, how well does it in that context?
No, it's a really good question. I don't think this is appropriate for big, large scale, because we can talk more about it. I think there's going to be problems. So it's more suited to a small number of collisions, which is kind of the robotics kind of problems that I'm kind of interested in. You don't have a lot of, there's not a lot of balls bouncing around when we're trying to plug something in. Okay, but the thing I wanted to, so yeah, you sort of picked up on probably this little bullet simulation here. There's no way I can simulate 1,000 blocks. I think it's going to fail. On the other hand, that simulation is wrong.
Yeah.
Because I dropped a bunch of blocks, and why are some of them bouncing, others aren't, right? And I know why, because yeah, exactly.
Yeah, do you think it could be possible to kind of read the source? Like, I guess this is more like valid and higher, but we have all these people building these incorrect with this, AI things, and then trying to make robots work on those, and you're like, oh, it's incorrect. How close do you think we get to real basis with the current Iola, trying to do 20,000 events?
So the answer is that time will come. Merle. You have to stop.
You have to stop because I would actually like to switch with you because you think that both sides have to say one. So I think you have to get the discussion outside in the break. Sorry for that.
All right, thank you for the introduction. My talk is prototyping composable simplification process for equation-oriented models using Modeling Toolkit. Yeah, so my core point today that I want. Okay. All right. So the core point today I want to talk about is Modeling Toolkit makes it easy to design new and better simplification algorithms because of its interactivity. So a bit on Modeling Toolkit, just like Modelica, Modeling Toolkit is a equation-oriented modeling language. You have the common connection paradigm, and here is how to define parameters and variables and specifying equations. All right, so the composability of Modeling Toolkit mainly arises from the fact that all the transformation process takes a X system and returns a Y system. X, Y are deliberately different because there are more than one type of system in Modeling Toolkit. So on the right, you can see that we have a PDE in a symbolic, represented in symbolic way. And in here, we are saying that we will use method of lines and finite difference to discretize the PDE. Using the symbolic discretization function, this transforms the PDE problem into OD problem. Now the periodic boundary conditions becomes algebraic equations, and then the interior of the PD becomes ODs. So running structure simplifier again on this OD system would remove all the algebraic constraints because of the boundary condition. So this is actually equivalent with the ghost point method when you are doing method of line discretization. Because the ghost point is really just writing all the equations down and then run alias-simulation by hand. Okay. And the next system is reaction network. So reaction network in here is being interpreted as a jump problem. Simulating jump problem to compute moments is actually really expensive because you need to simulate a lot of trajectories to collect the statistics. But then you can do the moment closure expansion to convert the jump problem into an OD system. And then this OD system would give you the first two moments deterministically. And in here, you can convert a SD system into a OD system that does the same thing, that expands the SD into ODs that computes the first two moments. Yeah, so in here, you can actually also convert the reaction network to SD system, and then from the SD system to OD system by using the moment closure package. So Scott yesterday was mentioning how he wants a nonlinear symbolic model order reduction pass. So we actually already have that. It's using the POD DEIM technique that takes the symbolic representation of the model and the snapshot of the model to run a nonlinear order reduction on this OD system. So it takes the OD system and then returns another OD system. And even better, we have a frontend that converts Modelica to an OD system. So all the previous transformation passes are actually usable for Modelica models. And all these passes are actually not written by me, the Modeling Toolkit author. And especially for the nonlinear order reduction, this is written by a master's student just over the summer, and he is actually also in Cambridge, so we can talk about that in more details as well. Okay. Oops. Yeah. So how are all these young contributors have easily added all these transformation passes without? They really didn't ask much of my help. So what makes MTK so hackable? And to explain that, I will show you how the structural transformation passes are organized in MTK. Okay. Yeah, so here we have RC model. And the Taring state is the intermediate representation for all the structural transformations in MTK. The Taring states in here, you can see that it consists of all the graphs, as well as the symbolic representation of the system. And I will explain a bit more on what this printing means. This is just saying that in the first equation, it contains variables 3, 4, and 5. And the green color indicates that these variables are linear in the equation. So you could possibly, it's possible to solve this variable from because of this equation. And as expected, because this is just an RC model, all the components are linear. So all the variables are linear in here. And on the right column, this is saying that the first variable appears only in the 8th equation. And this is saying that the first variable is the derivative of the second variable, and the second variable, the derivative of the second variable is the first variable. So these are all the information you need to do structural transformations. The dummy derivative plus actually runs dummy derivative and then Taring. So Taring gives you an assignment of what variable is being solved by what equation, right? So this color, this variable has a different color, which is yellow, I think. It's basically saying that actually the first equation is solving for the fourth variable, and then the second equation is solving for the sixth variable. And this is just saying that the first variable is being solved by the eighth equation. In here, there is a little integral sign. This is saying that the second variable is the actual ODE state that we need to integrate, which coincides with our intuition. So our system should really just be one ODE, and all the other states are solved because of all these linear equations. And the reason that we want to focus on the structural representation is not only because of performance. Working on integers is way faster than working on small expressions, but also that the symbolic information could be a bit confusing. So on the left, this is the system in the original dummy derivative paper. And the author used primes to indicate dummy derivatives. And you can also see a lot of people using primes to lower a second order ODE into a first order ODE system, right? And the question is, do you think that the two primes here have the same interpretation mathematically? Well, it's not quite the same, right? Because the derivative of variable x1 prime never actually appears. So this makes this a algebraic variable. But there is a derivative of x prime in here, so this is a differential variable. So that's actually not dummy, despite that it doesn't look like it. And if we think a bit deeper about what Turing really is, it's just a process that tells us which variable is being solved by which equation, right? So if variable number 1 is being solved by equation number 4, then you should have that mapping. But some variables are not reducible, so it could be nothing. So this variable, nothing would indicate that this variable is not solvable. All the differential variables cannot be algebraically solved, right? So we can encode that information by adding another singleton type called selected state. Then the classification of the dummy derivative just becomes that those are variables that appear to be differentiated, but then the lower differentiated variable is not a selected state, which means it's an algebraic variable. That makes it a dummy derivative. And in practice, this looks like that. So this is the original system in the paper. So after dummy derivative, we got assignment the first variable, the first equation is being solved for the 10th variable as such. And there are two integral signs in here, meaning that the 6th variable and the 11th variables are the actual ODE states. So those are the derivative of x2 and x2 itself. And that coincides with what the paper is saying. And then I will talk about alias simulation. Alias simulation actually happens before the dummy derivative, but for the sake of presentation, I thought it makes more sense to talk about dummy derivative first. Because of equation-oriented modeling generates a lot of connection equations. And those are in the form of A equals to B or summation of all variables equals to 0, right? And alias simulation removes those trivial linear equations. So originally, this model had 34 equations. And without running alias simulation, just running dummy derivative, we can see that we have 4 equations. But this system looks a bit weird, right? Can anyone tell why this is a bit weird? All right. So these two variables are differential variables, right? And then they are the only variables appear in the 3rd equation. So that means this system cannot possibly be an index 1 DAE, right? Because sometimes when running Pantelides, Panelides is only it's a bit weaker than checking the actual numerical run of the system. So sometimes it could give you a non-index 1 DAE. And realis-simulation will solve this problem because it removes all these trivial connection equations. Then the system is structurally analyzable, so it can reduce this DAE into actual index 1 group. We have even stronger realis-simulation. So normally in a lot of Modelica groups, it only reduces algebraic variables in realis-simulation. We can actually also reduce differentiated variables. So on the left, we have the system of DAE. And we can convert this system into the into this graph representation, right? Where all the arrows are pointing to the derivative of this variable, and all the equality signs are indicates the alias. So intuitively, you can complete you can complete the equality in here, right? And then complete the equality in here. So that will give us this alias, these aliases. And as expected, Modern Toolkit can actually generate and detect all these aliases automatically. And then the last thing in this talk I will show is plot parent state. So parent state, as I showed before, is the intermediate state, intermediate representation used in the simplification process. So you can use this function to plot the Turing state after each transformation. So in here, before the transformation, this is a DCPI model with a PI controller. You can see that it highlights the algebraic loop in here. So all the green squares means all these variables are solvable, and the black ones means it's not solvable. And the highlighted orange is the algebraic loop. So this is pre-simplification. And in here, this is after realis-simulation. So you can see, so you can run the algorithm and then see interactively how the system structure have changed. And then after running dummy derivative and pairing, you got just a system of all these, because all these variables are differentiated and they are not reducible. So this is the optimal you can do. And yeah, that concludes my talk. Any questions? Yeah.
Yeah, so you showed that you can translate Modelica model to the representation, is that complete or just partial or what is that?
Yeah, the author of the translation is actually there, so you can ask him.
So, yeah. I would say if you look at Yeah, I think everything is going very useful to the program or but so the summary is the continuous part of the work, but highly part.
One more question. You talk about this transformation, but there's kind of a sort of a tree structure that shows the overall thing. You show transformation one at a time, but you try to make sense of the overall taxonomy.
The overall transformation really is just expanding all the connections into actual equations, and then run realis-simulation and dummy derivative.
I was going to say, you have like PDE to OED, and you have delta OED, and you have OED stuff. I'm just trying to get a sense of the entire, you're doing a one-off here, all these things. Are they all just in the OED? Is that basically, is this X is going to be the OED system? Is that the only?
No. So for instance, in here, you can actually use catalyst to convert a reaction network into a SDE system, right?
It looks like maybe like Y equals OED in all these slides.
Well, I mean, so, you know, if we're looking at this, and if you said development space, you know, a lot of questions are how do you reduce back to the 80s, right? So a lot of people look into this, you know, as there's information for, oh, you know, these is good, these will be good, right? But, you know, if you have an OED system, you can directly simulate that SDA. If you have an SDE system, you can directly simulate that SDA. And there's no system you can directly, you know, each of these systems you can directly simulate on their own. But in the end, what we find is that some ways people who can the more sophisticated systems is to simulate it down. But there are other cases as well. So for example, you know, you can take these systems and represent it, try to solve what you can, right, using final fact theory. And these are other ways that we're taking. But you can always think about it as, you know, you standard systems, if you use standard type systems that you can have, and you let them be very solvable, you can try to discover what is the best mathematical programmation to solve this thing, and how and what are types of transportations to solve it. And that's what we've been going after all this.
Yep.
Sometimes when you do dummy derivatives, right, you can have singularities, and so you have to switch.
Yeah, that's not implemented yet. So you're asking for if MTK has dynamic state selection, right? We haven't implemented that yet, but it's in our priority list.
Okay.
Hi everyone, I'm Roshni Jacob, a PhD student here at UTD, and my advisor is Dr. Ji Zhang. So I will be presenting on the topic modeling and control of nuclear renewable integrated energy systems for electricity and hydrogen production. And this is a result of our project which has been funded by the NEO program by the Department of Energy. So this project basically involves integrated energy systems. So we started off with optimal planning, and then we also did optimal scheduling, basically the unit commitment economic dispatch using FESTID, which is the National Renewable Energy Laboratory tool. And then we also kind of looked at into the resilience of ideas. And down the line, although this was not there in the initial plan, we then thought of also considering the physical representation of the system and performing dynamic simulations to validate the control and coordination of the different subsystems. So without further ado, let me just jump right into the presentation. This is common knowledge that the fossil fuel reserves are rapidly depleting, and also there is an alarming increase of extreme weather-related outages. So it is without doubt that energy resilience and security is the need of the hour. So there are two facets for sustainable energy. One is energy diversification, and then the other is decarbonization. So as a result of when we consider decarbonization, increasing the renewable nuclear mix for power generation, that is currently happening in this current transition towards green energy resources. And if you look at the map that's shown over here, this is the state-wise representation in US of the change in carbon intensity over a period of 4 years. So there is a considerable change, and this will be continued to be pushed forward in the coming years. And nuclear is a very important player in this mix because it is a carbon-free energy resource, which is also reliable and provides stable energy. We need to also change the perspective of looking at energy sectors individually, and we need to adopt a holistic approach. So this is where integrated energy systems come into the picture. So by doing this, we can improve the energy utilization because we are using the same energy resources to supply various end users like electricity, transportation, heat, etc. So integrated energy systems is actually a multi-energy system. There are multiple forms of energy and different end users as well. In addition to this, the green hydrogen is actually at the forefront of many energy-related discussions. And this is because hydrogen is actually a very good flexible load resource. Basically, you can store excess electricity and thermal in the form of hydrogen, and also hydrogen is widely used in industry, transportation, etc. So you can see that in this graph over here. The hydrogen demand has increased over the years as well. Now, coming on to nuclear energy, the age-old concept of the nuclear power plant as the centralized baseload power plant has changed with the advent of small modular reactors. Small modular reactors are advanced nuclear reactors with a size ranging from tens to hundreds of megawatts, and it has the size of 1/10 of the traditional nuclear plant. So the features of SMR is that it's modular, scalable, and it is a clean energy resource, and it can be used for different applications, end users, like I said earlier. So this is very useful for integrated energy system applications. This is just like Twitter news that I think many of you must have already, you already know this, but the SMR that has been designed by NuScale has been approved by the Nuclear Regulatory Commission, and it will be soon demonstrated at INL, the Idaho National Laboratory. So the goal of our work was to design and model an integrated energy system which has nuclear power plant as the primary energy resource and also a renewable energy resource. Here we have considered wind power plant, but we also have studies where we are considering solar plant. And here it's supplying, and in this particular case study that we are presenting over here, it's supplying electricity to the power grid and then also producing hydrogen by utilizing both electrical and thermal energy. And the goal is to design the control system and to ensure a coordination between these subsystems while responding to the optimal dispatch signals, which you get from an external optimizer. And finally, we would also like to inspect the load following capability of the IES. So the IES, as is evident from the previous slides, is actually a system of systems, and it requires multi-domain modeling too, because we have different components in thermal, mechanical, and electrical components in our model. So we required a multi-domain modeling tool, and we wanted to do a physics-based modeling. So this is why we adopted the Modelica-based language on the Dymola platform. So and many of you are pros in using Modelica, but we have just done this over a period of a year and a half. You can say that we kind of discovered Modelica in the process. So the major thing that supports IES is that It enables it's actually an object-oriented language, so it facilitates modeling a system of systems, which is the IES. Coming on to this is actually the top level view of the IES in Dymola. And we have actually adopted this template from the transform library that has been produced by the Oak Ridge National Laboratory. So they have sandboxes, and we can modify the subsystems within these sandboxes as per our requirements. And so the transform library is actually a thermohydraulic Modelica based library that has been developed by ORNL. And then further, this has also been used by INL to develop the hybrid package. So both these are open source. We have used this because we are doing this project in collaboration with INL. And then we have also utilized the open source wind power plants library. So this is the model. This is the IES. There are different subsystems. So first off, we have actually the nuclear plant is the primary heat supply system that generates the heat for all the end users. And we have considered SMR because those are the advanced reactors, and it is based on integral pressurized water reactor technology. And here we have considered SMRs, 3 SMRs in parallel, and each has a rating of 160 megawatt thermal and 50 megawatt, and an equivalent of 50 megawatt electrical. So the SMR models are already developed in detail in the transform library, but all we had to do was to modify the control as per our requirement. So over here, it has 2 loops, the primary loop, which has the reactor core, and then the pressurizer, and then we have the secondary loop, which carries the superheated vapor. Basically it uses the thermal energy from the nuclear, and it carries to the other subsystems. Then we have the steam manifold, or it's also called as the energy manifold, and its function is to basically distribute the thermal energy between the different subsystems. So it has to dynamically allocate the thermal energy to the 2 end users. Here it is electricity and hydrogen production as per the demand signal. And this is done using valves, which are actuated by the control modules. Then we have the balance of plant. It actually consists of the turbine generator set that converts the thermal energy into electrical energy. And there are 2 particular valves which are of importance, which is the turbine control valve and the bypass valve. So that I'll discuss in the next slide. And we have the hydrogen production, that is our industrial process. We use the high temperature steam electrolysis plant. This particular model has been developed by INL. So we use this particular model where you need both electrical and thermal energy to produce hydrogen. Basically, it uses the hot steam in the presence of electricity, and it's split into hydrogen and oxygen. We have the switch yard with electrical interconnections to the power grid. The power grid is basically modeled as an infinite source or a sink, and it does not have a very detailed model. And then we have also used the open source wind power plant library. It's not very comprehensive in its electrical terms, but since we are using all the models, we just want all the models to work well with the hybrid library. And in the hybrid library, you are more focused on following the optimal dispatch signal. So so this would work for us. And then we have the supervisory control, which is responsible for the overall systems coordination and control. So basically, it accepts dispatch signals, and then it converts that into set points. And then these set points are sent to individual control modules. So you may see those green control modules, and those are actually PID-based controllers for different purposes. So in the next slide, I'll explain that in detail. So this is the control schematic. The small modular reactor or the nuclear power plant is basically having a steady state control over here, and it is made to operate at nominal conditions. Because the goal over here is to utilize the maximum available nuclear energy and produce electricity And then whatever is the excess or the remaining part we use for hydrogen production. And hydrogen is just considered as a flexible load resource. And then we have the power and pressure control. We have the valve control in the steam manifold. Like I said earlier, the job of the energy manifold is to distribute the steam to the balance of plant or to the high temperature steam electrolysis plant. And in the balance of plant, we have the power and pressure control. And the power control is basically performed by controlling the turbine control valve, and the pressure control is done by controlling the bypass valve. So these two are shown over here. And then we have in the hydrogen plant, or the HTSC, I think I'll call the balance of plant as BOP and high temperature steam electrolysis as HTSC for ease. So the HTSC can have two particular modes. It can be, if you know the power beforehand, then the steam is controlled accordingly. That is called the steam control mode. And if you know the steam that is, if that steam is predetermined, then the power has to be controlled accordingly. So there are two different modes. And then, like I discussed earlier, we have the supervisory control, which controls the coordination of all these subsystems. Now we have the control architecture. Here we get the input, which is the grid demand. In this particular case study, we haven't considered any input from festive. So in the next slides, I will discuss, that is one of our future plans. So here we assume that our input is the grid demand. So based on the grid demand, which is the input, we have to calculate the set points for the HTSC and the BOP. The HTSC set point is calculated in such a manner that you know the BOP max, that is the maximum available electrical energy, and then from that we deduct the grid demand, and also we have to deduct an electrical equivalent of the thermal energy required for this HTSC process. So based on that, we get the HTSC set point, and the BOP set point would be HTSC set point plus the grid demand, because the BOP is the sole electric generating unit over here. And then these set points are sent to the BOP module and to the HTSC module, and these modules have individual controllers for different functions. So these controllers are PID-based controllers, and they work on meeting the set points, and then the valves are controlled. And in the second case study, we had considered nuclear plus wind generation as generating resources, and the end users remain the same. So here you just also consider that while generating the HTSC set point. So this is like the simulation result with just nuclear generation supplying electricity to the grid and producing hydrogen. So like I said, we are operating the nuclear plant at its nominal operating capacity, which is 160 megawatt thermal, and there are 3 reactors. So you see that in the profile over here. We have the electrical profile. So in the electrical profile, the green signal is the grid demand that is supplied. And then as the grid demand, if you have a step increase in grid demand, there will be a corresponding decrease in the HTSC, so as to maintain the BOP are constant over here. So if you look at the mass flow rate, the mass flow rate profiles, let me just preface by saying that the negative sign basically indicates that the mass flow rate is outgoing from the unit, and the positive sign indicates mass flow rate is into the unit. So there's nothing to do with the magnitude, it's just a sign convention. So these are the mass flow rates into the, so if you see the mass flow rate into the energy manifold, it's basically at steady state, because the constant nuclear power is being supplied to the energy manifold. And then the energy manifold, basically the walls are functioning in such a way that the mass flow rate to the HTSC and BOP are changing accordingly. So these mass flow rate profiles, it resembles the power profiles as well. Now when you come on to wind generation, as you can see over here, we prefer to use the HTSC in all the studies. HTSC is a flexible energy resource. So you try to meet the grid demand and whatever energy balance. So you ensure that there's energy balance, and at the same time you're using any excess energy, or if there is less energy, the HTSC would be, the hydrogen production rate would decrease. So you can actually see that in the power profiles over here. The only difference is that here there is wind generation. So the variation in wind profile is actually reflected in the HTSC from 1000 to 5000 seconds, and then it reaches the maximum capacity of the HTSC, and then it has to be constant. So as the wind generation after 5000 seconds increases, we have excess generation, and therefore the BOP is ramping down. So case A is the previous case in these profiles. So you can see the turbine control valve and the bypass valve is acting accordingly, because as the wind, as the BOP has to ramp down, the turbine control valve mass flow rate decreases, and the mass flow rate through the bypass valve increases. And similar to the hydrogen power profile, you can see the hydrogen production rate over here. This is the mass flow rate of the hydrogen, so it resembles the HTSC power profile. In conclusion, we actually we started off with designing the integrated energy systems using the Modelica language, and then we see there is the load following capability. We ensure that the control and coordination between the different subsystems are working fine. Now our future work, this is something that we are working on right now. We are integrating the Festive, which is NREL's tool that's used for UCED, Unit Commitment Economic Dispatch. So we are accepting the input, the optimal dispatch signals from that, and we are passing it on to the IES model in Modelica, and then we'll get the actual power production or the actual hydrogen production when you give this dispatch signals, and then we are validating that. So that's the future work. And another thing that we are currently working on is also reinforcement learning based control of physics-based models. So this is just started now, and I think my fellow lab mate Jingbo, I think hers is the 5th presentation, so she'll give in more details about this. You can stay tuned and listen to that as well. So that's all about my presentation, and I'm happy to take any questions. Yeah, so that's the dependency. The small modular reactors are completely developed by Oak Ridge National Laboratory, and that's available in the Transform library. So we have utilized that model over here. Yeah. Thank you.
I'm Valentin Gavin. I'm representing a group of people here that work in a research project, and I'm representing a company based in France, Engie, who is a major player in the industry field. So we'll talk to you about an innovative concepts and application for large-scale and multi-mod system, and we have a specific use case application related to heat networks. So comparing to the previous presentation, we'll switch from the electricity production to the thermal production. So together with my colleagues, we'll share some information and a presentation about the Modelica project, and of course we'll talk about all the Modelica-based development that have been performed during our 4-year project. We'll speak also about use cases and application, and we'll finalize our presentation with a set of conclusion and future work. So I'm now presenting the Modelica project, but before jumping to this, I will just give you some information about the rationales of our project. So in Europe, we have seen a very particular summer with a lot of events. So heat waves, beluga swimming in the Seine River near Paris, wildfires across the country. So, and of course, besides all energy crisis in Europe. So these are all similar events as in 2018 when our research began. So we have seen here that all these situations can give us a set of ideas. So first of all, there are situations that call on us to be more inventive, to accelerate our influence on the environment and on the climate, and we have several tracks on which we can propose to go further, and these tracks are related to the heat production. Decarbonizing these activities and promoting alternatives to existing fossil power system, it's interesting now, and in this segment, district thermal energy networks are an interesting and solid alternative to decarbonize all these thermal energy usages. So this is the big context of our project. Now I'm switching the mic to my colleague Patrick Chambard from Dassault Systèmes, who will give you the presentation of the project.
Thank you, Valentin. I hope you can hear me, since I heard some difficulties a few minutes ago. So Patrick Chambard from Dassault Systèmes. So I was coordinating that Modelica project, and it was a group of eight participants. As you can see, NG, represented by Valentin today, plus some other big players such as EDF. EDF is also a major player in the industry domain in electricity production with a lot of power plants, especially nuclear, and research centers plus SMEs. So we made together a collaborative project that is funded by the French state and that lasted 3.5 years. So the idea was to address the energy domain, as you can see in the picture on the right side, the energy domain in different facets because of mainly pains such as difficulty to model, to compile, to launch, to initialize, and to run at acceptable time different models in the field of energy. So for that, we aim to develop new concepts, especially previous slide, please. Yes, thank you. New concepts, especially from INRIA Research Center, in order to analyze large model in perspective of multimode behavior. So also we made some work together with EDF on initialization schema, plus enhancements on the side of INRIA Research Center plus Dassault Systèmes in order to have a better capability to address large models. For that, we worked on Modelica and FMI standards. And we also made some validation based on 3 large case studies from NG, especially that will be described later. So about the global Modelica software results, just a few words, you can read the details. An ISAM-DAE prototype is a structural analysis approach, original approach from INRIA. So they made several papers on that for analyzing systems defined in Modelica in multimode level. Several enhancements in CATIA and Daimola apps with the increase of performance. An approach for model initialization made together on data simulation approach, data plus model together with EDF, and coupling with the ISAM-DAE prototype made by INRIA, coupling between Daimola and ISAM-DAE in order to commonly analyze with the tree structure definition how it should behave. Additionally, on the FMI, there was some distributed large-scale co-simulation based on EDF, industry partner, and some enhancements for FMI version 3. Additionally to that, we had some prototypes, library prototypes that were made by DPS, Eurobios, SMEs, and also a new PowerSys Pro ETF prototype in order to calculate the load flow, in fact, on grid of electrical networks to align this together with a global simulation. So that's it. Saying that, I will hand over back to Valentin in order to focus more precisely on the heat network context.
Thank you, Patrick, for this. So, beside the software development, our consortia also conducted research and developments on the dedicated Modelica library, dedicated to the heat networks, to district thermal energy models. So on this, we model and simulate several components that are commonly seen in district thermal energy networks. We have here a screenshot of the library that was developed during the project. So we have seen that we see that we have traditional components which are very close to the Modelica standard library components. So, but into these basic components, we have different assemblies which are more related to the district energy system market segment. So these models were developed by the project team from operational specification and from the field requirement that were provided by ENGIE. So the libraries break down in several fields. The fields which are the most related to the heat network market segments are here. They are addressing components such as heat exchangers, valves, and so on, but also different assemblies or examples, complete models of or parts of district heating networks. So this library was developed by DPS, who was a partner in the project, and is now operational, and it was used by the project members. Now I will go further with the use cases presentation and the application. The idea here was to integrate these operational specification and from the field requirements into the models that were developed by the team. To do this, we have used several information and several data that are coming from real systems. So we have used data coming from a network which is based in Lyon, France. It's situated here on the map. It's an existing heating network that was commissioned in the early 70s, and this network is quite representative for big networks in France or in Europe. So it's 20 kilometers long with 78 substations, and we have here an equivalent of 9,300 dwelling units. In the future, this network will be extended, so approximately 45 kilometers of additional networks are already planned, and currently this network has an energy mix composed by a biomass boiler, gas boilers, but also waste heat from nearby incineration plant. So once we had this information from the field, we use the bottom-up modeling approach, which is not very far from current development made by Long and other researchers from National Renewable Energy Laboratory, United States. So we have break down the overall model or system into several blocks. So we have the customer loads, we have the substations, the network, so the distribution, and then the production. So between all these components, we have different connection points that are represented into the Modelica library. So on the customer loads, we have used real-time data coming from our measurements. we have several periods of measurements from 2018 to 2019, where heat demand, temperature, mass flow, valves opening, and so on are recorded and integrated into the model. We have then the network, so the pipes. We can see here the overall model with 4 geographical sectors that were modeled, and at the end we have the heat production with the different production systems that were presented earlier with their main characteristics. So we have proceed to the modeling of this network, and we try to reproduce the results of the whole system as in the operating conditions. So we have model, as I mentioned earlier, the system. We have here different screenshots with a focus on the waste heat power plant or on the substation system, which is connecting the distribution network with the building. And from this entire model, we have simulated all the behavior on a yearly basis, and we have compared the simulation results with the measurements coming from the field. So Engie is the operator of the district network, and the data was available to do this. So based on this simulation, we have also calculated several KPIs. Temperatures, mass flows, and energy consumption, and we have compared these results with data from the field. So we have a quite interesting and a good alignment between the simulated results and the reality. And we have, of course, seen some difficulties, especially during the simulation phase, especially with the CPU time. But we have managed to progress on this and to make significant progress in order to tackle all these issues, but also issues related to the compilation or to execution of large models. Now, I will give the floor to my colleague Charlie Duprat from Dassault Systèmes, who will give you a more detailed overview and who will show you a short demo of the network modification and modeling in 3D Experience platform.
Yeah, correct. Thank you very much, Valentin. Can everybody hear me well?
Yes.
Great. So carrying on, Charlie Duprat speaking. Myself, I am part of Dassault Systèmes, so who was part of this project, obviously, and I was acting as coordinator on one of the work packages, the one we're presenting today, focusing on the heat network industrial applications. Based on what Valentin has just presented to you, you have seen that we have developed a library, we have developed new capabilities in terms of modeling and simulation of heat networks in this very case, and we figured it'd be good to apply this to a concrete case and put it, leverage our internal product at Dassault Systèmes, the 3D Experience platform, to develop a demonstrator to be able to better showcase the capabilities that were developed in the context of the project. So this is what we did, and we chose a very simple scenario to make it as understandable and clear as possible, which is to make it very short, where in the context of a south of France city with 17 substations, so slightly smaller than the full extent heat network, right? 17 substations only, and we are in operations phase of this heat network, and due to, for instance, the addition of a new part of the city, new buildings, new infrastructures, there is a need to install a new substation, therefore to change the whole system. And in order for us to be able to adapt the system, well, before we need to conduct all the analysis, we need to do an engineering review, we need to update the design, and we need to validate this. And at this point, we're going to leverage this new capability we have been developing. So this is the scenario. There is an entire demonstration and video that lasts around 20 to 30 minutes, which is very long. So obviously, we're not going to use that today. I'm going to show to you a very short version, which is 5 minutes long. It's already long enough. So all the, let's say, high-level parts about project monitoring, project control and execution, dashboarding, and so on, which are relevant, will not be shown today. So we will start focusing on, let's say, in the snake you have under your eyes, starting from step number 2 or 3, and really focusing on the engineering modification, the engineering change, and then the use of this new capability within the 3D Experience platform to validate this modification. So Valentin, if we can switch to the next slide, please. Thank you very much. And we may want to start this video, yeah.
Let me see if I can manage this.
By the way, we have about 3 minutes left. Can you hear me?
Yes, we can hear you.
Move on to the next presentation.
Okay, so I'm gonna do this very, very quick. Maybe Valentin, if that's the case, can you just fast forward to maybe approximately 2/3 of the video? And we're just gonna focus. So yeah, I'm not gonna comment at all due to lack of time. Yeah, can you just skip to 2/3? So a bit later in the video. So here, basically, we have it's an all integrated design, right? So you have the architecture, the functional and logical architecture, you have the 3D PNIDs, you have all the design integrated in a single environment, which empowers collaboration. And on top of that, obviously, you have the Modelica part that is put into music here. So if we can fast forward a little bit more, Valentin, to, yeah. Okay, here we're updating the PNID, relevant, but we have no time to comment this. A bit later, yes, this is a 3D update, right? So we're updating the 3D design directly based on what's been done in 2D. And finally, yes, a bit forward, please. Thank you. Okay, right there, we can leave it there. Great. So now it's the relevant part in the context of this project. Here, we have updated the 2D models. We have validated this update. We have updated the 3D models. And now, based on this update, we have generated automatically the Modelica, so the behavior model of the new part of the system. So the substation, pipings, fittings, valves, and so on. And we have integrated that into the pre-existing entire behavior model of the entire heat network. So we've put it at scale, and we are now simulating this network to make sure that everything goes right as planned, as per the requirements. And so what is being verified here is that the outputs, the values are in line with the expected requirements. And what's interesting here is that thanks to the use of this new Modelica library, in combination with 3D capabilities and so on, we're able to easily visualize the results. We're able to analyze in detail the results. We're going to see that just afterwards, but most importantly, we are able to put it at scale and to simulate it in a reasonable amount of time on a, wider scale model, right? 17 substations, with no performance issue and with pretty good accuracy capabilities thanks to this new library once again. So if anyone's interested, of course, we'll be happy to comment further this demonstration, but due to lack of time, we're going to stop there for today.
So it was a research project that was conducting during 4 years. So we have explored several innovative concepts for large-scale and multi-mode systems. On the modeling track, several new techniques for systems initialization were made, and of course we have improved different capabilities of the Modelica systems with libraries, tools, and FMI approaches. On the industrial track, of course, all these developments were used to support the design studies, to better understand the behavior of the complete system. Dimula software was used and of course was improved in order to be able to address other industries in this field. It was an interesting collaborative opportunity around a topic which is still actual nowadays, and of course in the next months and years, we are planning also to continue our work and to pursue this development and address again larger systems with multi-mode analysis, compilation, and simulations and simulation. So that's all on my end. Of course, we are at the end of the presentation. We would like to acknowledge all the supporters of the project, so BPA France and the French state in global.
Thank you very much.
Hi everyone, my name is Jingbo Wang. I'm a first-year PhD student at UT Dallas. Me and Roshni are all from the Design and Optimization Lab under Dr. Jie Zhang's supervisory and over in UT Dallas. Okay, so for today's presentation, we are going to talk about the reinforcement learning-based control of integrated energy system using OpenAI Gene. So next, I'm going to talk about the background. So why are we looking at this? From the IES point of view, originally the nuclear power plants have traditionally served as a centralized plant for base supply. However, with the development of the smaller modular reactors in recent years, it has brought the nuclear utilization for microgrid more closer, together with other forms of renewable energy systems such as wind and solar. As we could see, so in the presentation on the right-hand side, so originally there's a large base nuclear power supply, and nowadays there's smaller modular reactors, or so these lower scales can be directly scalable and can be used for the microgrid systems, together with the other renewable system forms like wind and solar. Then it forms like a complex IES systems. For our work, we have used some of the open source packages, such as Hybrid, that is developed by the INL Lab, National Lab, and also the Transform by Oak Ridge National Labs to create the integrated energy system. So with the complex IES systems, now it comes to the question, how are we going to managing those? That also is a question that we ask ourselves. What is the best way to control this complex system? Is the artificial intelligence more suitable, or the traditional controllers such as PIDs already satisfy this purpose, or using both of them? That's into our motivation. So when we think about renewable energy systems, it is such a complex system that introduces multiple uncertainty from different source of energy systems. So we are thinking probably with the reinforcement learning algorithms that can be leveraged to cope with these uncertainties. So for our objective as a first target, we want to use the artificial intelligence model in conjunction with a physics-based model. So here is a very simple illustration. For instance, if we have the reinforcement learning agent here, together with the balance of plant that is that will be responsible for electricity generation, and then to fulfill the grid demand. So with these systems, we want to understand like how it will perform comparing to the traditional IES control strategy. All right. Next, I want to talk about the overall environment that we have been using in the Modelica environment. Okay, here's a simple illustration of what we have been using from the hybrid. So as you could see from the left-hand side, we have these smaller modular reactors. They are stackable, so depending on the grid demand level, we can stack the SMR as needed. And then it comes out as a thermal energy going into a steam manifold. Then it can either go to turbine for electricity generation, or it can go to other renewable source, like for hydrogen production, or for other source like battery storage. So in these models, all of these submodels like BOP or HTSE, they have been using the PID for valve control. Sorry. What we are going to do is to replace this PID with the RL control mechanisms, as it's more autonomous and can be developed online for real-time control systems. Next, I'm going to talk about the actual experiments that we have been implemented in the balance of plant. So here I'm going to give a short introduction on the base plant that we are using. So the model environment is Dymola 2022, and the model invested with the RL agent is a balance of plant. For details of the model, we have the ideal turbine. All right, I will try to use a laser point here. So we have an ideal turbine here, and we have condenser and also the heating source. So these together come coupled as the balance of plant. And then it have this TCV and BV as the turbine control and also bypass valve control. So in the red circle, that's the PID controller that's originally implemented in the Modelica language. And then we are going to experiment with the reinforcement learning. Why are we doing this? So from a modeling standpoint of view, testing the viability of co-simulation with the artificial agent. And also with this complex systems, we want to understand how complex or the effort that's required for training the agent with such a system. From the control point of view, we want to compare the PID performance and the intelligent agent. So next, I'm going to talk about the AI part structure that we have been using. So it's basically the RL framework that has the environment for us that will be the BOP. And then it will be interfaced with the Python Dymola interface to observe the simulation results, and these will be like the state observation going into the OpenAI gene. So the state will be understood from the agent side and then gave the action. So this loop is continuously when we gave a different electricity demand. In the left-hand side, we have illustrate more details about what state we are observing from this balance of plant. So for power produced by the BOP, that's normalized based on the maximum power capability. And for the action side, we will be gaining action for turbine valve opening and also bypass valve opening. They will be positioning from 0 to 1. 0 means fully closed and 1 means fully open. And on the reward side, we will be comparing the generated power and also the demand power. So the goal will be minimize this power. And on the reward side, we will use 1 over the error plus the delta. Delta will be like very small values that's compensate for divided by 0. All right. And for the learning framework, that's actually the DDPG, Deep Deterministic Policy Gradient algorithm that we have been using. It contains 4 neural networks and 2 pairs that's targeted as the main network that uses Q network and also policy networks. So the neural networks gets a state from the plant, and then it goes to the policy networks to understand to get action. And then this action and state together will go into the Q networks to calculate the Q value. And also there's a soft update from the other neural networks that observes next state once the first pair goes through, and then calculate target Q networks. So these updated value will then going back into the main neural networks to update the weighting factors. Yeah, so these are the general functions that's being used in DDPG. Okay, so I will go into some slides regarding the preliminary results we have been seeing. So from this slide, we have randomly choose electricity generation required. So over here, that's a demand that's generated by the agent. So for instance, if it asks for 130 megawatts, as we could see the green line, originally without any control, it will have a default values with 408 megawatts. However, with the iteration of trainings, then the agent learns how the valve will be open and closed, and then we could see that the electricity generation will be closer to the required electricity. As this is only a preliminary results, we know that the agent performance still need to be improved. So I'm going to talk about the training progress and also some challenges we have been facing. So overall, the agent will generate a normalized electricity demand while learning how to control the valves to meet the power demand. And we have performed trainings with multiple steps, with multiple episodes. So as you could see in the left-hand side, the plot with good iterations that has the reward in the y-axis. So it basically swings from 0.5 to 1. As we could see, as iteration progress, that the reward is going towards 1. So actually, that's one of the sample we have been used to test out the valve opening positions with the electricity generation that we shared in the previous slide. However, in the right-hand side, we can see that there's still examples of field iteration that still we need to figure out what is the problem here. So for taking an example here, so for the lower green lines, that the agent start with a fairly low score, but it stays here and doesn't going to increase. Even though we only plot for 10 iterations, but we have also observed this with longer iterations as well. So from this preliminary results, we have seen that with multiple episodes that indicate a trend that going into convergence for agents learning the valve positions. However, there's also episodes that we see failures. All right, and then taking into two of the examples of the challenges we have. For instance, during training, that the agents become stuck at boundary conditions, like it starts at valve opening at 1-1, and it basically gets a 0 reward, but couldn't learn from it. Then it will stuck there. So this is some challenges we need to look at. The second part is the DDPG agent is actually working from -1 to 1, but the valve position is actually opening from 0 to 1. So we have to match the working zone of the agent as well. So with these two issues being fixed, we would expect the agent will be perform much more sufficient, and eventually we can try to test out with the entire IES. That's all from my side. Thank you.
Are you using Modelica gym or are you using bipolar gym? Which one is
We are directly using OpenAI Gym. I try to use the Modelica Gym, but I face some difficulties directly from that package.
Because you need to use FMUs. So
I have used the FMUs, but yeah, there's.
So Ole was visiting me when they implemented that stuff. And then he couldn't continue because he's Ukrainian, so they're in war.
Yeah.
But, what we did is that we replaced the FMU part with the Dimola API on the original Modelica gym.
Ah.
So now there is a Dimola gym.
Yeah.
Yeah.
Are
I
you?
can send it to you.
Basically, we did start off with a Modelica gym. We read Modelica flavor. So we wanted to do reinforcement learning on ideas model. So we started off with Modelica gym, and then we saw that we need to use OpenViews, FMI, and then after discussions with INL team, they suggested that using FMI and putting on the current model is very complicated. So we decided to adopt the Dimola API because it's already available. And then we also came across the Dimola gym.
Okay.
Yeah, so we did see that.
But are you using Dimola gym?
Not right now. Yes.
Because it's very tricky with the Python Dimola API. So it took us a while to figure out how to get it to work properly, to interface, and to run the simulations correctly, all these things. It might be work for your it's not so well documented in Dimola Python interface. So you will see it. And the other thing, those models are, I played with them because I'm currently taught really good. So, are you running them in DAE mode or not? No, you don't know what it is?
No.
Okay. So if they're running slow, you gotta enable DAE mode.
Oh, okay. Yeah. No, these are not. This is actually, I think the DA one is enabled.
Okay.
Considering that's a very common.
Yes.
I thought, so what do you teach
Thank you.
I'm Akhlaq bin Aziz. I'm from the Department of Nuclear Engineering, University of Illinois. So my work is on modeling and integrated energy. I'm a second year graduate student, but I started my work from this year, February of this year. So my work is modeling and integrated energy system in Open Modelica to utilize the output of a reactor for producing energy and powering a desalination plant. So today I will discuss on these 4 topics mainly: the motivation for the work, then modeling the integrated energy system, then the industrial multi-effect distillation desalination plant, and the controller system for this plant. So the main motivation for this work was, microreactor is being built in the campus of University of Illinois for the first time, in US and maybe in the world. So, and there was a reactor at Atkau plant in Kazakhstan that was powering our desalination plant and also for power generation and district heating, and it operated nicely and safely for several decades. So, so we have chosen this as a model or as a reference from where we have decided to start our modeling. So to make it simpler, we have divided this whole Atkau plant model into 4 different blocks. So these are the 4 blocks. So one is the fossil burner block on the left side, then the reactor block. The reactor block, the output of reactor goes to one well-stage turbine, then another turbine in the second loop, and then that steam powers the desalination plant and produces potable water after feed water treatment that is stored in a tank, and then the same amount is pumped back to the reactor. So this is my model. So I have started. So my focus right now is on the reactor block or the desalination block, which I have modeled in Modelica. On the right side is the model. So I've been using Open Modelica all the time, but my professor is always insisting me to move to Dynamo because it's more easier and sometimes very difficult to debug in Open Modelica. So on the right hand side, the desalination block is basically a black box. I found from previous literature like how much is energy required for per unit desalinated or potable water. So the energy coming from the turbine, the steam, and knowing that energy, I could calculate how much desalinated water it was producing. So it was initially modeled as a black box, like very simple model, but later I developed on that. So for the initial models, some results I got. So just in the results of the integrated energy system, I'll just talk about the desalination output. So here the total input is the blue one, the red one is the feedback, and the difference is the potable demand that is fed to the tank for storage and future use. So after modeling that part, then I started modeling the desalination plant in details and further details, not keeping it as a black box. So this is an industrial multi-effect distillation nuclear industrial desalination plant used in Chemco plant or ACTO plant. They used a 5-effect plant. So I'll just go briefly to this schematic figure. So on the right hand side, seawater is coming in, passes through the condenser, pulls the steam coming out of the final effect, and most of the seawater is rejected. Only 85 to 90% is accepted and passed to the main plant, depending on the season or the distillate demand. That is clean for suspension on the seawater, and then passed to the deaerator. While going to the deaerator, a scale separator adds some sealing crystals. The function of the sealing crystals is that when the seawater goes through evaporation and distillation, scale formation occurs. So that deposits on the heat transfer areas and might reduce the heat transfer coefficient. So sealing crystals actually attract or absorb those scales and have similar composition. So that doesn't affect the properties of heat transfer so much. So because it absorbs those scales. And then it goes to the deaerator. The function of the deaerator is to remove the oxygen from the air so that to minimize the corrosion in the components of the effects. And in each deaerator, some steam is bypassed from the effects, and the incoming seawater is heated, and it goes on and finally enters the fast effect. So since it's very difficult to explain everything in details in such a short time, I will just go through the first effect and the last effect, what's happening. The remaining effects are almost similar. So in the first effect, heat steam is coming in from the turbine that is used to boil off a fraction of the seawater that's coming in from the deaerator, and the heat steam condenses and goes back to the reactor, and a fraction of the seawater is boiled off, that is the vapor, and a part of it is bypassed to the deaerator. And since a fraction of it is boiled, the concentration increases, and we call it brine. This brine goes to the next effect, and the vapor also goes to the next effect. The vapor then boils a certain fraction of that brine again in the next effect, and this process continues to subsequent effects. So this is the last effect on the condenser. So last effect, the output of brine has nowhere to go, so it goes to the scale separator, where the scale of the sealing crystals is separated, and the scale gets concentrated and is added to the incoming seawater for the reason I said before. And the steam is bypassed to the deaerator as shown, and the condenser just condenses the final steam, and the distillate is collected downwards. So I have modeled this whole thing in Open Modelica and tried and ran it with some practical values, and I'll show the results. So these are my results of my desalination plant model. So I've given a seawater flow rate, a sinusoidal seawater flow rate into my system. On the upper right hand side of the figure you can see. So the middle blue line is the distillate output, and the lower red line is the brine output. So in the lower figure, it shows the concentration of the brine coming out of each effect. So as the brine goes from one effect to another effect, a part of it is boiled also. The concentration slowly increases. So in the final effect, we can see sharp rises in the concentration for drops in the seawater flow rate. So this is natural because the steam coming is fixed, but if seawater flow rate decreases, then a larger fraction of it will boil over and the concentration increases very much. but there is a problem. The problem is there is a operating limitation, operation limitation or operating criteria for the plant. The final seawater concentration or the brine concentration cannot exceed a maximum value, because if it exceeds a maximum value, then the sealing crystals cannot absorb the scale, and the scale deposits on the heat exchange area. So to solve this problem, I have to design a controller, because I cannot allow the limit is 60 gram per liter. So the final brine concentration should be between 50 to 60 gram per liter. So to solve this problem, so that it can be operated like following the restrictions, so I have designed a controller. So I will go through some briefly about the controller. So for the controller, I kept the output brine concentration for the calculations, like the brine concentration that I want. So the range is 50 to 60, so I kept it at 55. I didn't keep it at exactly 60 because the controller used some plane equations that were found or the plots were found using many different result sets. So since it's a fitting, so there is some error. So that's why I kept a little bit low, and I ran many different cases and saw it's always within the range. And I didn't keep it lower to be more safe, because in that case the efficiency of the plant will reduce, because I will get less distillate if I keep the highest concentration at a lower value for the controller. Then the steam temperature, I kept for one steam temperature, each steam temperature, I ran the whole thing. Then the controller, depending on the steam temperature, controller chooses the set of equations and then does the calculation. I will show it later. And the seawater temperature doesn't have a lot of it has very negligible effect, so it wasn't considered as a variable, because whatever the seawater temperature is, the deaerator or the deaerators ensure like the incoming seawater reaches to that desired level. So the independent variables were seawater concentration and distillate demand. Seawater concentration plays the biggest role, because if the seawater concentration is very high, then to reach that fixed set concentration, I can boil off only a small fraction of the seawater. If the seawater concentration is low, then I can boil off a larger fraction of that seawater. So that's why it's a very important variable there. And distillate demand also, it will vary depending on the season of the year, time of the day. So that's why it is also variable. And depending on distillate demand, if the distillate demand is high, then for that seawater concentration, I will need higher seawater flow rate. If it's low, then I need lower seawater flow rate. And for that seawater flow rate found from seawater concentration distillate demand, I found the steam required, because for that seawater flow rate, I need to boil up that seawater flow rate to get my distillate, and for that I need some steam. So depending on the seawater, I will need a certain amount of steam. So I will go through two important cases. These two actually summarize the whole controller. First, if the distillate demand is low. So if the distillate demand is low, then the seawater flow rate required will be low. So as a result, not low amount of steam will be required. So there is a certain amount of steam coming in from the turbine to the desalination plant. So if the steam requirement is low, then the steam requirement will be fulfilled by the steam coming in. That the steam required is less than the steam coming in. The excess steam will be rejected and used for distributing or other purposes. And hence, the seawater flow rate is coming in. I have enough steam to boil off that seawater, so my distillate demand will be met. The problem will arise when the distillate demand is high. So, if the distillate demand is high, then the seawater flow rate required will be high. I will get the seawater flow rate required from the block 1 on the upper right hand side. So, if the seawater flow rate required is high, then I will need a very high steam flow rate as well to boil off the seawater, which I will get from block 2, the bottom right here. So, if the steam requirement is very high, it will cross the amount of steam coming in from the turbine. So, the steam requirement will not be met by the steam coming in from the turbine. So, that will be a problem in that case. So, in that case, what the controller will do is, it will allow the steam coming in to pass through, the whole of the steam coming in to pass through, and for that steam, it will calculate the seawater flow rate that can be allowed to the desalination plant. The entire seawater flow that was required cannot be allowed, because I don't have enough steam now to boil it off. So it will allow that only allows seawater flow rate that I will get from block 2, and for that seawater flow rate and seawater concentration, I will get a new distillate output from block 1. That will be my distillate output. This will be definitely less than the distillate demand because I don't have enough steam now to boil that seawater. So these are my outputs. So on the left hand side, if the distillate demand is not very high, so I have distillate output is equal to distillate demand because the steam coming in from the turbine is around 10, the steam required is lower. So I am passing all the steam required to the desalination plant and excess amount is rejected. So I get all the distillate that I require. Seawater allowed is equal to seawater required because now I have enough steam. And if the distillate demand is very high, in that case, steam required is higher than steam coming in. So in that case, if you calculate the new seawater allowed, and the bottom figure, right hand side, you see, the seawater allowed is lower than the seawater required. That seawater allowed will be allowed to pass now, and that will give a new distillate output, which is on the top right hand figure, the red line. So the demand was around 50, but we get around 42. So that difference is not made now. So the controller does this thing. So on the top right hand side, the controller, I have coupled it with the desalination plant and made the desalination plant block. This block is again put into the integrated energy system to make the whole model work. So I have compared my results with the question proactive about nuclear desalination plant. So the plant operates with all the restrictions met because the controller ensures that the maximum concentration is not exceeded. The concentration in each effect is comparable to the plant. And the boiling temperature or the temperature at each effect is kept similar to the tempo plant. And distillate output of the plant can be matched easily from my plant also because if the distillate is high required, then I can increase the seawater or the steam input and get that required distillate or reduce it. So because I haven't considered any restriction for the pump that is pumping the seawater. So my future work will be to integrate the desalination plant and the current integrated energy system, which I am doing. And also the reactor block I've shown in the first figure will be replaced, is now a furnace heating a boiler and a boiler is producing steam. That will be replaced by reactor. So I will model the physics and kinetics of the reactor in Modelica, which I have started. I'm modeling the kinetics of the reactor and then I will put those equations into that part and ensure a proper reactor is modeled as the control mechanism controls the steam also. So that when the distillate demand is very high, it can change the level of steam and provide that as well. And finally, develop an automated ideas for the reactor included for the whole system. So that's it. That's my presentation. These are references. Thank you very much.
So I'm not aware of anybody who's modeling desalination.
Yes, I am. So you come doing the research, but not. Yeah, I mean, there are some people that have done that, but I think what you did looks like actually better. The other models that I know are not really good.
So I wanted to encourage you to talk to your professor to see if you can make it open source because it's a very valuable resource. There's some projects in the Middle East that are looking into using not steam but renewable energy to do desalination too, but you still need steam.
Yeah, for renewable energy it will be very difficult because producing 10 megawatts of energy will require many solar plants.
You gotta boil
solar
water.
cells, sorry.
You gotta boil water anyway.
Yeah, so and a microreactor is that we are planning to put in our campus is very small, like the size of a traditional generator. It would fit inside a truck also. So.
Very nice.
Yeah, thank you very much.
Think about contributing. I think it will be useful for other people when they're starting. to look at these problems. At least they have a starting point. They don't have to reinvent the wheel again.
Yeah.
At least I want it.
One comment, the transform library, which was mentioned.
Yeah, I think this is in Dynamo obviously, but I was doing it open Modelica, so.
I mean, we're currently working to make the transform library also work in model impact. It works mostly actually. So I think there's a fair chance most of it will.
Okay. Thank you for your feedback.
Any other questions?